Yeah, I know. It's like,
all right, a couple of announcements. And then a security alert. Oh my gosh, this application has been what the heck? This application has been, okay. Better not disable my application, buddy. All right. First of all, lab. Most people enrolled in the Monday lab section. There is also a Wednesday lab section. I need some volunteers so I don't have to voluntold people to move to Wednesday. Right? I can handle a maximum of 16 in a section. We have like 22 in, I think, in, if not 22, pretty close to at least 20 in the Monday session. So it will be more equitable and better for you if you are in a lab section that has, the right number of people or fewer. So in any case, ideally, we would have, balanced sections with the same number of people in each section. But if I have to voluntold people, I will, because it's that important. The other thing about lab, as some of you already know, and I will have a list that goes around that you'll sign up for access to the labs. Lab sessions are going to be, you'll be required to be there for our scheduled lab session, even though you will be doing independent research and often coming in outside of those hours. What we will do in lab, once you start actually doing your research, right now we're going to ramp up so that we can give you some tools and start you thinking about what projects you're going to do. Each bench is going to do a different project. But every week you'll come into the lab session and we'll have a lab meeting. When you actually work in a lab, you have a weekly lab meeting. Heck, when you work in an industrial lab, you have a daily lab meeting. But we're going to do more of the academic style. And in the lab meeting, usually there's somebody who presents what they've been doing, but mainly it's about everybody talks about what they are doing, what problems they're having, and there's a group think about where they can go to help with their research. So that's what we're going to do. We're going to talk about your project. You'll talk about when you're starting, just trying to find the materials, when you're working on it and things aren't working out right. Those are all things you'll talk about in a lab session at the beginning of the lab. All right. So that was my laboratory session announcement. Another announcement is I have a super, super heavy schedule this semester. I have an open door policy. If my door is open, stop by, and I will make the time for you, unless I have a scheduled meeting or somebody's going to have an appointment scheduled, in which case I'll let you know. However, I do not have a closed door policy. Usually, and I will keep doing this, I keep my door open as much as possible. But this semester, if you see my door closed and you can tell, hey, I know he's in there, don't knock unless you have an active arterial wound. All right. I make as much time as I can for you. I will keep the door open as much as I can, but there are times when I just have to shut it and get some things done so that we can serve everybody. Okay, so if it's open, absolutely cool. If you make an appointment, absolutely cool. If it's closed, say, well, Dr. Goad maybe he's in there with asleep. And I'll admit, there are times when I take everything out of my pockets and I lay down on the floor for 15 minutes just to take a mental break. So, all right. Big breath there. All right. So I've been recording all of these lectures. I got them all posted. Everything except for lecture 1 is posted. And of course, today's lecture. So let's see. Any questions about where we're at so far, how this is going in this course? People want me to go faster. People want me to go slower. Okay. Nobody cares what I do. All right. So, come on, fancy control. So we're going to talk more about energy today. We started this conversation about delta G. We can do delta E too, but we're talking about delta G, Gibbs free energy, and specifically the change in free energy. Because the change in free energy is the amount of energy available to do work. And doing work means anything from moving to transporting things across the membrane to storing energy so we can do work somewhere else later. All of those things are work. And it's never 100% efficient. When we take energy and capture it and store it as high energy molecules, we lose energy as heat. Energy that's made the entropy of the universe greater. That heat has gone off to the universe. And then when we break a bond to use that energy to do the work, we're still not going to capture all the energy. So we're going to release more heat. Okay. We're going to define free energy. Now, how many of you remember delta G equals delta H minus T delta S? Yeah, we're fun stuff, wasn't it? We're not going to worry about that when I say define free energy. We're going to define free energy at a little higher level than worrying about the details of entropy and enthalpy. You should know those things, but that's not what we're going to do here. And we're going to distinguish favorable versus unfavorable reactions. Probably this is all review. I could probably just go home now and you'd be just fine, right? No, nobody wants me to do that. Okay. Interpret energy diagrams. That's pretty basic. Explain why cells need energy currency, why ATP, or GTP, or NADPH, or all the other energy carriers. We'll talk a little bit about that. Now, ATP is kind of the default energy carrier, and so we'll talk a lot about how an ATP enables work. All right, so we already said that contrary to over a century ago, there is no vital force that can erase all the rules of physics and chemistry because life does its own thing. No, we know now that life follows those strictures, those rules. We also know that not all reactions are favorable. Yet we need to have unfavorable reactions as well as favorable reactions. We need to have both of those reactions. Favorable or not, we need to make those reactions go. And energy determines biological possibility. This idea of favorable and unfavorable and linked reactions all comes into what our possibilities are. It has to do with the energy landscape. All right. So covalent bonds. To make or break a covalent bond is quite a bit of energy. And some covalent bonds are higher energy bonds than others. And we're going to talk about ATP, and we're going to talk about the phosphates and the phospholine hydride bond and why that is such a high energy bond. All right. But we have to have these molecular interactions. They need to be reversible. They need to be fast. So we use non-covalent interactions. Very, 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 very rarely do you see covalent interactions. Now, you may see an enzyme that's got covalently linked subunits, but that's acting as a machine. I'm talking about the reactions within its active site. Even structurally, microtubules are constantly being assembled and disassembled in this whole treadmilling process. Okay. Structural changes, that is conformational changes, whether it's a conformational change of the cell, a macrophage chasing a bacterium, or even just the conformational change of a transporter, changing so that it can transport a package from one side of a membrane to the other, that requires energy. The energetic changes go with chemistry. All right. So all these chemical reactions, we talked about catabolism, we talked about anabolism. Here's our building blocks. And so we take in these materials. In fact, we take in all of these materials, we break them down to make exactly the ones of these that we want. So it's a process of breaking things down and building things back up. That's part of what a cell does, this anabolism and catabolism. All right. I want you to think about this. Stability is not the same as inactivity. Cells are active all the time unless they're dead. Cells work at the edges of equilibrium. But cells want to maintain a state of disequilibrium, so it's near equilibrium. Equilibrium is boring because nothing's happening. Cells need things to happen. And there's this high turnover, so there's this balance. Even though we're at near equilibrium, the cell is very active. And the cell can be very stable. So free energy. This idea of free energy determines the direction the reaction is going to go, not the speed of the reaction. In fact, my match demonstration the other day, that was a spontaneous reaction even before I struck the match. It was spontaneous, but did the match just burst into flames? No, I had to overcome the activation energy barrier. Has nothing to do with the rate of the reaction. And it's not intention. These are probabilistic things. We talked about this milieu of the cell, this viscous fluid that we call the cytosol, or the nucleus plasm, or the cytoplasm. We can use all those terms depending on what we're talking about. Of these things randomly bashing into each other constantly. And these molecules coming together at the right angle, at the right velocity, all of that is all probabilistic. But the numbers are huge. All right, so let's talk about this idea of equilibrium first. You guys know, hopefully, that a negative delta G is what we call a downhill reaction, right? So if I have negative delta G, actually I have a slide illustrating this, so I'll just wait on that in a bit. I'm going to release energy that I can use to do work. And if I have a positive delta G, I'm pushing things up the hill. I'm storing energy. I'm rolling that boulder to the top of the hill so that when I need that energy, I can give it a little shove and it rolls down the hill and I can use that energy, right? But equilibrium is when delta G equals 0. And that's when things are going back and forth, but there's no net change. And for cells, that's not really typically good. Well, there are some points of equilibrium. We won't get into all those fine details just yet. But what this means is if I make this graph, I want you to think about this. Here's my Gibbs free energy on the y-axis. Here I have my reaction progress on the x-axis. Let's say, I know it says delta G, or it says G naught. We're not going to worry about all of that stuff. You can do that in physics again, yeah. If I have the reactants and no products, my reaction's going to tend toward equilibrium. It's going to go in that direction of hitting that energy minima. This is energy here. This is the minimum energy, that right where equilibrium is. Equilibrium doesn't necessarily mean I have equal things on both sides, but it means the rates are going at the same rate. Conversely, if I have all these products, enzymes, for the most part, aren't directional. They don't care which way the reaction goes. They facilitate the reaction. So that if I have a bunch of products with no reactants, again, I'm driven toward equilibrium. So the cell uses this, right? I can drive reactions just by the relative quantities or concentrations of reactants and products in each reaction, depending on each reaction's point of equilibrium and all that. And they're naturally going to be driven to equilibrium. So I need to maintain some bit of disequilibria to keep reactions driven. That makes sense? All right. So here's our energy diagram. Vocabulary, exergonic reactions, just a reaction where delta G is negative. You are releasing heat. Well, you're releasing energy. Some of it's going to be heat. Hopefully you get to capture some of it and do work. When I struck my match, I was pretty much releasing all of it as heat very inefficiently. An endergonic reaction is one that requires the input of energy. Now, all reactions require an input of energy. Let's look over here. To get my exergonic reaction, this little delta G right there, I still had to input energy. I had to overcome that energy barrier. All right? And when I put this, when I go the opposite direction, I still have to overcome the energy barrier, and that's always there. Okay, those barriers are important. Excuse me, let me get a little. I've already been talking for about half an hour. I just recorded a thing from my advanced cell and molecular biology class just before I came in here, so my voice is already starting to feel it. All right, so pretty much we're beating this whole delta G thing into the ground, but negative delta G means we're getting energy out. Positive delta G means we're putting energy in. Hey, there it is. I knew I had my animation in there somewhere. All right. Why barriers matter? Why is this activation barrier so important? Well, for one thing, it keeps our reactions from running away. It means I can have matches in a box that are metastable without having to worry about them burning my house down. Nitroglycerin has a activation energy. It's not as sensitive as people think it is, but it's still sensitive. But a good shock is enough to overcome its activation energy. It's not as stable as my match. It releases a lot more energy than my match. So it gives us stability and it stops runaway reactions. But it also gives us leverage for regulation. We can use enzymes to lower that energy barrier, and we can regulate those enzymes so we can regulate what that barrier is in time based on the activity of the enzymes. We can turn the enzymes on or off. That gives us ability to regulate reactions. Does that make sense? Okay. So what I'm trying to do here is not give you delta G equals delta H minus T delta S. I'm trying to get you to think how this really applies to living systems. So, uphill reactions are how you store energy. When we make ATP, that's an uphill reaction. I talked about my favorite, one of my favorite molecular machines, ATP synthase or synthase, depending which version you want to use. And it just blows my mind that every one of my mitochondria has these little turbines spinning around, thousands of them on every mitochondria, millions, billions of mitochondria inside of me, all doing that, storing this energy. And they're transferring energy from an electrochemical gradient, which we created. We'll get to how we create that electrochemical gradient, to mechanical energy, back to chemical energy. It's really a cool process. So what we're talking about is the transfer and localization of energy. When we have coupled reactions, the net delta G must be negative. If you don't have a net negative delta G, you ain't gonna do the reactions, right? To drive an unfavorable reaction, you have to have a favorable reaction that has a delta G that's negative. It's negative enough that you can drive the coupled reaction. And you can see how this, if we think of this as a vector, even though it's a little bit curved, but if you think of these as vectors, you can see the magnitude of the negative vector is much greater than the magnitude of the positive vector. And that difference between those vectors is the energy we lose as heat that we can't do work with. All right. Now, this is an illustration from your book. And being me, I'm I look at it and say, yeah, it's a pretty cool illustration. Then I look at it and go, well, you know what? The artist forgot some things because you lose heat there, there, there. I'm losing heat there. I'm like losing heat there. Probably more places than that even. But why I think this is important is you've been showing these diagrams and we make them simple systems so you can understand them. But now you got to start taking these concepts and how do they apply in these simple, even these simple systems? How am I doing? I'm already tired. Okay. So favorable reactions drive unfavorable reactions. We have a net negative delta G. I already said that. And if we have a net negative delta G, it's possible for us to do work. We can drive that unfavorable reaction. So here's an example of glutamic acid. And just to remind you guys what amino acids look like, and yes, you should be able to draw the amino acids. Now, this is not about memorization, but every one of you can draw the A, B, C, D, E, F, G, H, I, J, K, L, M, N, P, the whole alphabet. You know that. Because that's the basis of how you communicate. That's the symbols you use to communicate, to read, to write. Amino acids are the alphabet. Okay. So, quick review on amino acids. Glutamic acid, and they show it here. I'll draw it here in just a second for you. But here's my glutamic acid right now. So when I draw my amino acids, I like to show them as being ionized. Now, if I have a chain of amino acids, that is a peptide, only the ends are going to be ionized. And we can say that this is protonated. This amine group's been protonated. So we have that positive charge there. And then that guy goes to our alpha carbon. And this is the carbon that the side chain came off. This is the carbon that makes the difference between what amino acids we're talking about, because whatever's connected to that carbon is going to determine the amino acid. For right now, we'll just put an R group. And over here, I can draw the H or I cannot draw the H because the H is implied. Carbon always has 4 bonds. Well, I've only got 2 bonds there, so I must have another bond here, and I do. Okay. This carbon on a single amino acid is the other ionized portion. You could draw this with an OH, and you could draw this as H2N. At biological pHs, this gets deprotonated, this guy gets protonated. So that's our general formula for an amino acid. Now let's make this guy into glutamic acid. Oh my gosh, I should go and show that it's being deprotonated as well. It's an acid. It donated its proton. All right. But so I'm going to start. This is what I'm going to start with is my glutamic acid. But I also need to make glutamine. That is, I need to take this carboxy group and turn it into, put that amine group on there, make it a glutamine. And to do that, we have this activation step where it's actually kind of cool. We phosphorylate this guy, put a phosphate group there. So we lay some heat there, putting that phosphate group from it, moving it from ATP. We broke that high energy bond in ATP, and now we've made this activated thing. And this has more energy now because we just gave it more energy. And then we can use that energy to replace the phosphate group with our amine from ammonia. Okay. So we have used ATP as the currency of our reaction here. So ATP, there it is in all its glory. Well, in my bad handwriting glory on my fancy dancy monitor. So what is this thing about ATP? Well, of course, we have our ribose, and it's ATP, so it is RNA, so we do have that hydroxyl on the number 2 carbon. And we have our adenine here, and the O should probably be a little bit lower down, so but yeah. No, that oxygen is right there at that. That's not a carbon there. All right. So we have these 3 phosphates with these phosphoanhydride bonds. Why are they high energy phosphoanhydride? Why are these things high energy bonds? We got a couple things going on here. The first is to look at all these negative, 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 all together. Do like charges attract or repel? Repel, right? So right away, I'm putting all these charged oxygens all close together. They want to get away from each other. But I also have another thing going on here. Resonance. Although we draw this double bond here, that's not really the way things are. It's a cloud of delocalized electrons. The electrons in that valence are actually in resonance here. If I have just a straight up phosphate, inorganic phosphate, I got my electron cloud is resonating between all of those things. I can't actually say, oh, that oxygen is a double bond oxygen. Those electrons are in that resonance cloud. I'll put that there so that I can tell, oh, there's those electrons. So I got to account for those electrons. But they're not static. But, okay, so here is my resonance structure. The more resonance I have, the lower the delta G. If I constrain the resonance, like here, this guy can't be involved in the resonance. It's got 2 bonds already. He doesn't have any room for any electron cloud floating around it. So immediately I've constrained this to this. And then again, this middle guy, and I've constrained it even more. That should actually be on that side of it. My little cloud should be here. The electrons can basically resonate between those 2 oxygens. As I limit resonance, I increase delta G. So these phosphoanhydride bonds have charge pushing on them, and we have pushed the resonance clouds tighter and tighter. When we break those bonds, the resonance increases, lower delta G. Where's the difference in delta G go? Energy that we can use. Like charges get to repel. They get to get away from each other. Lower delta G. Does that make sense? All right. Yes, you need to be able to draw this. Again, I don't see this as memorization. Well, it is memorization, but it's not anything different than the ABCs. We're using a different language here, and you need to be able to converse in that language and read that language. But I want you to start looking at structures like this and start thinking in terms of resonance and charges, looking at the structure, not just, well, Dr. Goad says I have to memorize this. Oh, my. I want you to actually look at the structure and think, because that's what you need to do to be a biologist. Ah, there it is. Yes, you need to draw this. And more than that, be able to explain it. I might not ask you to draw this. Now, here's the difference between genetics. On genetics, I would have said, this will be on your exam. May be on your exam, probably will be on your exam in some form, not necessarily as drawing it. May not be on your exam at all. But you need to be able to explain it. If I put it on the exam, it's probably be along the, if let's say I did put this on the exam and I wanted you to draw it. It wouldn't be draw the structure of ATP. It would be draw the structure of ATP and explain why it matters and what the key points are. And the truth is the drawing would be the least part of those points. All right. So we have phosphoanhydride bonds store energy, and we know how they store energy now. And now we can see how we can, here's it's using sunlight, but ATP we think of as the universal currency. But we use GTP as well. A lot of nuclear transport uses GTP instead of ATP. We have G-coupled proteins, that's GTP instead of ATP. It's not the only activated carrier, but it's a very, very common one. And we have our phosphoanhydride bonds shown in the book. And there's our, now I don't like this diagram because you have to kind of look at it. What they're saying is to go from here to here, this is a positive delta G. I'm smushing everything together. I'm pushing those charges that don't want to be together. I'm smushing those resonance clouds and limiting resonance. And going from this to here, breaking this bond, is my negative delta G. All right. So we link exergonic reactions to endergonic reactions. We need to drive endergonic reactions. This is just the same thing as saying the net has to be a negative delta G. You have to have a big enough exergonic reaction or reactions to drive your endergonic reactions. And so this is our activated carrier. And this is an important diagram insofar as, hey, it doesn't say ATP. ATP is a common carrier, not the only carrier. And of course, we said this enables synthesis, transport, movement, being able to move energy where you need it, when you need it. That's what the energy currency is for. We talked about the mitochondria being the powerhouse of the cell. That's great. It churns out all sorts of ATP. But I need that ATP at the edge of my membrane where I'm trying to transport stuff. I need that ATP in my muscles where my actin and myosin are. Can't even think of the parts of the muscle now. All right. So this gives us the ability to make a whole bunch of currency, a lot of stuff that you can think of the mitochondria as the ATM. It spits out the currency, and then we can use that to do work. All right. So we talked about phosphoanhydride bonds. And phosphoanhydride bonds, like all bonds, it's really about, I don't have it up here anymore. It's about the electrons. Why do they have negative charge? Because they're missing, they have extra electrons, right? Missing there. They got deprotonated, and the proton was not a proton, it was a hydrogen, so it left its electron behind, and the proton left, and so they got an extra electron. The resonance is about electrons. Chemistry is about electrons. Everything on that chart is about electron clouds. Well, not everything, so you can look at the nucleus too. The nucleus only matters as to what element we're talking about. The electron cloud determines the chemistry, right? So this brings us to oxidation and reduction. So if I have, here's my atom and number 1 and atom number 2, and I put these together with a covalent bond. This could be a hydroxyl, right? And in this case, there's a partial positive charge here and a partial negative charge there, which means it's partially reduced and partially oxidized. So let me review what oxidation and reduction is. Oxidation is when you lose an electron. Now, this doesn't lose an electron, but the electron has a higher probability being found over here, so it's partially oxidized. It lost that electron. Reduction is gaining an electron. The easiest way to remember it is, let's say I have a sodium atom. Right? Actually, let's make it a sodium atom and a chlorine atom. In order to make this from two toxic things, sodium metal, if I let it touch water, it explodes. Chlorine gas, you don't want to be in chlorine gas. That happened in World War I and II sometimes. Two toxic things. You wouldn't want to hold sodium metal in your hand because the moisture in your hand would react with it and that would be bad. But if I oxidize the sodium, that is, I take an electron away from the sodium goes from a ground state of 0 to +1. And that electron takes the chloride that has a ground state of 0 to -1. The oxidation number is negative. That's why you can remember which way to go. Maybe it doesn't work for you, but the easy way to remember which does which. So, chemistry books like to talk about half reactions because you have to have the electron. So if you oxidize something, something got reduced. We're not going to worry about that half reaction stuff, all right? But this means we can carry energy in the form of oxidized atoms, specifically high energy electrons. In the form by these chains of oxidation and reduction, we can transfer the energy of electrons. And that brings us to here. I looked at this last time just before I ended the lecture, but here's carbon dioxide, what we exhale. When I lit that match, carbon dioxide was coming off that match. So was carbon monoxide and some other things. But had I had a stream of oxygen blowing on that match, so I got 100% combustion, those sugars in the match, that is the cellulose, which is just chains of glucose, would be turned into carbon dioxide, water, and heat. So carbon dioxide is kind of, look at this, it's low energy. Is carbon dioxide flammable? No, I can use it to put fires out. Okay. Methane. You going to put a fire out with methane? Probably not. It's part of the oxidation reduction. This is reduced. The more reduced it is, the more energy is in there. There's high energy electrons in there. When I light methane up, if I get complete combustion, I get this. All right. They're both part of the same series of oxidation and reduction. So when you think of oxidation and reduction, I want you to think of, did I put that in? Oh, I did not do that. Okay. I want you to think of energy. And these oxidation, we talk about the electron transport chain, oxidation, reduction, oxidation, reduction. We're moving up and down these chains of oxidation reduction with other molecules than carbon dioxide, methane, and methanol. I mean, methanol is pretty flammable. Formaldehyde, I've never tried to set formaldehyde on fire, and I wouldn't recommend it. And I've never tried to put formic acid on fire, but there you go. All right, let's talk about some of these other carriers. NADH or NADPH. I didn't put that all the way. Oh well. We'll talk about NAD and NADPH. Now, when I was first learning this stuff, I looked in the book and I saw this big structure and I was like, okay, it's just this big thing. Okay, that's all I need to know, the big thing. But it's not that hard. Hey, look at this. That's just like adenine, and there's my ribose, and there's my phosphate group. Hey, look at that. It's all the same. The only thing is I replaced this adenine with a nicotinamide ring. Life is modular. We use the same molecules over and over to build different structures. If you can draw ATP, this is not a stretch for you. And you can see there's my oxidized versus reduced form. This is my NADP plus. And then I reduce this guy, get rid of that double bond, put that guy there. And yes, that's a hydrogen, which is a proton and an electron. Think of it this way. You move the electron there and the proton comes to join it. Yeah. So there's my H minus and going in there. All right. So this idea of oxidation and reduction is a way to carry energy. And we talk about reducing agents for anabolism and oxidizing agents for catabolism. I'm not worried about that so much. I'm right this point trying to drill in oxidation reduction energy, high energy electrons carrying energy, activated carriers. Coenzyme A, oh, that was another one. Oh my gosh, look at that structure. I just, pretend I don't have to look at it. Hey, look at this. Does that look familiar? Why do I make you learn to draw the structure of ATP? To torture you? Well, that's only the part that makes me happy. It's because it's the vocabulary. It's the alphabet. All right. And then we got this little bit here. We've got some carboxy. Look at that. That looks a lot. Well, I'm not going to go there. This simple chain here, we have a self-hydral, or a high energy bond. It's not a self-hydral bond. We have a high energy bond here, and there's our acetyl group. So when we talk about acetyl-CoA, yeah, we focus on this part of it, but this is really not that complex of a structure if you can draw ATP. You can look at it and you can interpret it pretty quickly and easily. It doesn't look so scary anymore. FADH2. The electrons it carries are slightly less energetic than NADP electrons or NADPH electrons, but they're still high energy electrons, carries 2 electrons. And look at this. This is a little different, and this is just highlighting you, showing you where things get oxidized and all that, how we go from FAD to FADH2. The point is life is modular. Chemistry in biological systems is modular. We use the same subunits to build different structures. All right. I forgot why I put the polysaccharides and glycogen in here now, but that's another course. These are all high energy electrons in here. That's where we take our NADPH or NADH, and we move those electrons and we pump protons to the side of a membrane through the electron transport chain, and that goes to the ATP synthase. But when we capture sunlight, we kind of do the opposite thing, and we store that sunlight as high energy glucose, and you can make glycogen out of it. And I forgot really why I put this in there last night, but that's okay. RNA. So I was just basically talking about, I remember talking about you use ATP to build these things. You use ATP to build nucleic acid chains. Proteins. You use ATP or actually GTP in proteins when you're using the ribosome, but that's okay. You use activated carriers to be able to make these bonds, to store the energy in the, why am I blanking on it? Oh, this is embarrassing. Peptide bond. Peptide, hard word. All right. ATP, AMP. Oh, yes, this one. This is a cool strategy. We talked about cleaving off that terminal phosphate all the time of ATP. You see all these reactions, we cleave off the terminal phosphate of ATP. But you can cleave off the 2 terminal phosphates and then cleave them, and you release twice as much energy as you do from just cleaving off the terminal phosphate. So that's the other thing that's really cool about this triphosphate structure is we actually have its modular and how much energy we can extract from it. So the other, and I'm going to close with this, the other thing with having ATP, I meant to bring my match in a sugar cube today, and I was going to light the sugar cube on fire. That's always fun. Fire's fun, right? But when you do that, I have to hold the match there on the sugar cube for a little while to overcome that activation barrier. And then I would set the sugar on fire, and it would drop all of that. And assuming that I had complete combustion, say we do it in an oxygen atmosphere, they go really fast in an oxygen atmosphere, but we get complete combustion, then we wind up with CO2 and water. What ATP and these other carriers are all about is extracting the energy stepwise, not in one fell swoop. So I can extract the maximum amount of energy. What if I use this to make ATP? Well, I would use this tiny little bit of energy of it to make my ATP. I'll get there. Come on. This tiny little bit of energy to make my ATP. And the rest of it would just go as heat. Our body temperature would be a lot more than 37 degrees Celsius. But I do this stepwise reaction. This is one of the things to take these free energy and put it in these activated carriers, whether it's ATP or GTP or NADP or NADPH or FAD or FADH2. We can extract the energy a little bit at a time and be more efficient and grab all that energy from that sugar molecule. Because glucose in the sugar cube, that's sucrose, I know, glucose and fructose, but glucose is glucose. So this is why we go through all the metabolic processes of glycolysis and oxidative phosphorylation. I'm done now. And there was great cheering. Yay, he shut up, yay. Please do, if you can, if your schedule allows, please move to the Wednesday lab.